Hi, everybody. Our next speaker is Jairong Wu, and she's currently a postdoc at Quran Institute of Mathematical Sciences at NYU, working with Larzana, and is a member of LEAP. She is looking for new ways to improve air-sea flux parameterizations in climate models using a combination of observational data, high-fidelity numerical simulations, and data-driven methods. Previously, Jairong obtained her PhD at Princeton University, advised by Professor Luc Dakey. Dakey, is that correct? Okay. And her thesis focused on the dynamics of ocean surface waves in the context of air-sea interactions. In general, Jairong's research interests include fluid dynamics, waves, turbulence, ocean physics, climate modeling, and computational methods.
Thanks, Caitlin. Hi, everyone. My name is Jaron. I sit at NYU and primarily work with Professor Lorazana. But this work is sponsored by LEAP, and we have also one of the co-PI, David John Ganier, who is involved. So our goal is to develop a data-driven probabilistic air-sea flux parameterization. So the air-sea flux that I am focusing on are these sensible and latent heat fluxes and momentum flux. So we want to express them in terms of the surface layer state variables. So including wind speed, atmospheric temperature, humidity, sea surface temperature, current speed, etc. So these fluxes are basically given by turbulence fluctuation in the surface layer. That's what we are trying to parameterize because they're not resolved. And we need these air-sea flux algorithms in both an online and offline setting. So in an online simulation, you would take your prognostic variables of the surface layer and compute fluxes and then kind of pass them between the atmosphere and the ocean. And in an offline sense, people also work heavily on constructing these flux products. So you have these green variables, the surface layer state variables that are more easily observed by either in situ or satellite remote sensing. And you use them to compute maps of fluxes, which are hard to resolve, to measure. So there are very few direct in situ measurements of fluxes. So what people have currently been doing is use these so-called bulk algorithms to compute fluxes. You express basically the flux as some coefficient times the magnitude of the relative wind speed times some quantity that is the difference between the atmosphere and the ocean. So for wind stress, it would be the velocity difference, for sensible heat flux, the temperature difference, and for latent, the humidity difference. So these coefficients are then obtained using physics-based theories like Monod-Nabokov theory, but there are very important parameters that are empirically fitted to the sparse in situ observations. So basically, this results in slightly different versions of this bulk algorithm used by different models and institutes, maybe fitted for different subsets of data. You need a kind of iterative algorithm to compute these coefficients, and there are some ad hoc corrections. For example, for the gustiness, which I was told that are actually very important when you actually use these algorithms. So basically what I'm saying is they're physics-based, but there's a heavy empirical flavor to it. And so this is a source of uncertainty in our current coupled GCMs and also in flux products. So you can see here in this work, they looked at what if they changed the flux algorithm in computing, in putting out these flux products, and you will have a pretty big difference in even the zonally averaged flux values. So there have been sensitivity studies on what will happen when we change these flux algorithms. And the other issue I want to point out, and which is also what this work is aiming at resolving, is these flux algorithms are designed to represent the mean of the flux given some input state variables. But when you actually look at the observational data, you see that there's some spread around that mean. And this is not just from measurement uncertainty. Of course, part of it is from measurement uncertainty, but part of it is from our inability to include all the relevant variables in our inputs. So you can think of it as there are some hidden variables, for example, the ocean surface waves that we're not using as inputs to the flux algorithms. And so as a result, these flux values are not kind of deterministically, cannot be deterministically represented. So you're always missing some variability. And the thing to resolve this, some people have tried to put back these hidden variables. For example, you include an additional C state in your flux algorithms, but then that means you need to know this additional input, either from observational point of view, measure them, or solve them in your model. And the other way of doing it is to have some kind of stochastic parameterization where you say, I don't know what the source of variability is, but they have some maybe correlation in space and time, and we just want to use stochastic parameterization to represent them. Yeah, so that's about kind of the variability that we might want to recover. And so what we did, we took some data from NOAA PSL. They have about 10,000 shipborne measurement, a direct measurement of fluxes. So they actually measured the very high frequency fluctuations of these velocity component and took the mean. So every sample is an hourly averaged eddy covariance measurement of the flux. And these data remain our best kind of source for calibration of any flux algorithm, because at this stage, we still don't have high fidelity numerical simulations that are mature enough to directly give us these flux values over a wide range of inputs. So we use observations, and what we did is we now, instead of a deterministic flux algorithm that would give you one value, a point estimate given the inputs, we're now assuming that given some inputs, our flux is following a distribution conditioned on the inputs. And in this case, we use a very simple Gaussian distribution. So it has two parameters only, the mean and the variance. So we use neural nets to estimate the mean and the variance. So yeah, we have this parametric distribution condition on inputs, and then we estimate the parameters using neural networks. And here are some references for how this kind of parametric probabilistic framework is applied to some geophysical problems. Yes, and how we are able to optimize the neural networks, we basically try to minimize the neg log likelihood loss, so to maximize the likelihood of observing these data points. So here is an illustrative example, and here are some synthetic data. You can think of this as wind speed, this as momentum flux. So I generated some samples, and the neural network is able to learn over epochs both the mean and the spread around the mean at the same time. Yeah, so basically we then did this for a problem of 5 inputs and 3 outputs. Here is illustrating a 1D example. So our choices of inputs ended up being the wind speed, temperature of air, temperature of ocean, relative humidity, and surface pressure. And again, we're operating in a pretty data poor regime. So we also did careful cross-validation, early stopping, etc., to make sure that we're not overfitting. And so as a result, we now have improved statistical estimates of these means. Here is showing my neural networks in orange and the classic bulk algorithms in black. So for all 3 fluxes, momentum, sensible heat, and latent heat fluxes, the neural network is having, I say, slightly better correlation with the observations. But it's also worth pointing out that any of the evaluation metrics we have kind of in terms of bias and root mean square error seem to be pretty sensitive to what region you look at. So one thing I should point out with this data set is kind of half of the samples are actually in the tropics, because this is initially they took all these research crews to look at kind of air-sea interaction processes in the tropics, which is a big focus. But unexpectedly, somehow the statistical score, for example, for sensible heat flux is the lowest in the tropics. And this is consistent for both ANN and bulk algorithms. So basically, to summarize, we have an alternative estimate of the flux using neural networks. They're actually giving pretty similar predictions, I would say, compared to traditional algorithms. We are failing where the traditional algorithms are failing as well. But maybe in some regimes, we're seeing a slight improvement, for example, here. And this to be further investigated whether this improvement is significantly important for example, representing latent heat fluxes. And the other part is now we're explicitly estimating the uncertainty around that mean prediction. So we also took a look at like, for example, the predicted uncertainty structure. Here is like a 2D input space where here is wind speed, and on the y-axis is the temperature difference between atmosphere and ocean. So this plot is the predicted flux value, and this is the predicted uncertainty of this predicted flux value. So you can see, for example, the uncertainty is higher for higher wind speed. And this is to be expected because we actually have very little measurement above 15 meter per second wind speed. So on the very right, I'm showing the scatter plot of the data density, basically. So yeah, we don't have that much data beyond this regime. So we cannot hope for too much for the neural networks, but at least what we're seeing that the extrapolation is smooth. So you're not doing something crazy outside the training data. Here is a comparison of the prediction of ANN2 core. Again, you're seeing the structure is pretty similar, but because we're not assuming some functional dependence, so the predicted sensible heat flux is not strictly down gradient. So there is some difference here. So this, I think I talked about this a while ago at LEAP. So maybe some of you remember it. So what is coming next is, I think, new. I haven't talked about it here yet. So we implemented this newly learned flux algorithm in a single column model of the upper ocean. So it's kind of expected that the upper ocean interact the most with atmospheric forcing. So we want to see, at least in a simplified setting, what a changed flux algorithm will do to the upper ocean state. This model is a single column model. So it's basically ignoring advection. So you only have these kind of diffusion type of equation where the time evolution of your velocity, temperature, and salinity are given by vertical mixing and some kind of Coriolis forcing. And this vertical mixing is also parameterized, but it's not the focus of this test to look at these turbulence parameterization. We are looking at the effects of the surface flux parameterization on this system, and the surface fluxes are imposed as boundary condition, but they also affect some things in the vertical mixing. And the model is run in a forced way, so we take observational record from this particular site called Ocean Weather Station Papa. And it's a famous site for calibrating vertical mixing schemes because seems like there is very little horizontal advection happening at this particular region. So we take the record of the state variables and then we compute fluxes. So orange is ANN and black is our baseline core algorithms. Again, so here is a more detailed plot of the time series. So for example, it's basically the difference is pretty seasonal. For example, in the summer, these two track each other pretty closely, but in the fall, maybe in some high flux time periods, we're seeing some difference between the neural network and core. And another interesting thing we can do with this probabilistic framework is now we can have stochastically perturbed flux series. So instead of predicting only one deterministic value, you are sampling from the predicted distribution. So you have an ensemble of stochastically perturbed fluxes that you can now use to force your upper ocean. Yeah, so this is some implementation detail, but basically that assumption that I mentioned before, a very weak horizontal advection, is an assumption. And actually from the flux data, we're seeing that if you ignore horizontal advection and keep forcing the system without correction, your state will actually drift away because of a net flux imbalance at the surface. So what we did is monthly restart of the simulation to kind of reduce this drifting. And we focus on the response of the state to different flux forcing in each month. And here is a result, basically a composite color map of results from 4 years, where I can find continuous record of observations. So the hatched points are where we don't see statistically significant response, but where we're seeing actually the response is during the summer. We're seeing slightly cooler SST, sea surface temperature, and deeper mixed layer depth. Yeah, and this seemed to be independent of which turbulent vertical mixing parameterization we're using. So these two vertical mixing parameterization give the same response, although with slightly different magnitude. And I will skip this and talk about this probably the last slide of the results. So bear with me. There's the spread in ensemble members. As I was mentioning, I ran 20 ensemble members with stochastically perturbed fluxes. So blue is the deterministic run. The magenta is the mean of these 20 ensemble runs, and the shade is the standard deviation between ensemble members. So what we see both in these time series plots and also in this color map is so this mixed layer depth. When this mixed layer depth jumps up is during the spring. The upper ocean goes from a well-mixed state to a stratified state. So this restratification, well, we know this restratification happens in the spring, but what we're seeing in the ensemble is that there is a particularly large spread around the mixed layer depth in this time, meaning that so this restratification process is sensitive to perturbation in a turbulent heat flux leading up to that event. Yeah, so in summary, we proposed a probabilistic model for ARC flux. This is very different from the traditional approach, so it will start to change how people think about this variability they see in observational models, in observation, sorry. And we used a very compact ANN. These are actually very small ANNs. I forgot to mention maybe 16 neurons in the hidden layer. So it's pretty compact. It can be easily implemented because we are using the same type of bulk inputs as traditional models. And we have two pieces in this model. One is the estimate of the mean. This can be used in a similar way to traditional algorithms. And we're finding slightly better statistical correlation to observations. And there's an additional piece, which is the variance, and this can be used for uncertainty quantification purpose and for online stochastic parameterization. So we did the implementation in a single column forced upper ocean. It was a choice of mine whether to test this in an ocean model or an atmosphere model, because we kind of expect to see a larger response in the atmosphere model to change in sea surface flux parameterization. But just personally, I don't have the expertise of running an atmospheric model. But hopefully in the future, we can test this in not just atmospheric model, but also coupled general circulation model. So that we can see now when this stochastic noise get coupled to other horizontal advection and coupling processes in GCMs, what will happen to the large scale variability, and if it could help us address some of the bias in current models. And here is the paper manuscript, and I can take questions. Thanks.
Hi, Jerome. Thank you very much for a very nice presentation. I was curious to know if you if you think at some point to try to perturb the atmospheric boundary layer, if it's forcing, and then see how in turn that drives the spread in the ocean mixed layer. I think that would be very helpful.
Could you specify, do you mean perturb the atmospheric
Yeah, like wind or boundary layer mixing, or or it parameters the surface like Charnock parameter at the wave interface, like all these sort of parameters that control the structure of the boundary layer from the atmospheric side. Just a curiosity. I mean,
yeah. So it would eventually what matters from the ocean's perspective is these fluxes. So what you hinted at, I think, is approach to perturb the parameters that exist in current flux algorithms. What I did here was I built an algorithm directly to estimate the fluxes. So I bypassed all those roughness parameters, the instability shape function that is hidden in this box that's used to compute fluxes. So I didn't go into all those. My model directly estimate the flux. So a perturbation would just be applied to the flux itself instead of these parameters that are inside bulk algorithms.
Like, I think it would be very helpful for if you could make believe the atmospheric community could really use a lot these results. Because I think these results are very important. So I think if you could make this link, it would be even more relevant for people that care about atmosphere.
Yeah, I think like from what I understand, if I start to change the sensible and latent heat fluxes into the atmosphere, it will actually change quite like the modes of variability, say MJOs and stuff like that. I just haven't tested in a general circulation model.
Very interesting. I'm wondering, from your schematics, it looks like you trained two separate networks for the mean and the standard deviation.
Yeah.
Even though their losses are computed together.
Right.
Did you test just predicting everything with one network, or we're just curious?
This is a really good question. We did this because during training we have realized that if we train the mean prediction first on mean squared error and then go on to train the variance network with already trained mean, it seems to give slightly better statistical scores in the mean prediction. So we are doing like a two-step thing. In the second step, we are still allowing the prediction of mean to change, but the mean has like been through a first stage of training under MSE era. This is, I think, because there is some ambiguity of whether you put you put some variability into the prediction of the mean or the uncertainty. So if the network is able to capture more the variance already, then the predicted variance of the Gaussian will be smaller. I don't know if that makes sense. So if you train them together, there's some wiggle room.
Good. Let's wrap it up. We'll give another round of applause. Thank you so much.